torques. If you have more than one force, you have to calculate the torque of each one. So what you get is a series of competing torques, some of which are clockwise, some of which are counterclockwise. Maybe some of them are zero. It's possible for forces to exert no torque. One way that could happen, even if you have a force, one way it could happen is you have no leverage. Another way is you're pulling in the wrong orientation. So you're just pulling radially to the circle and not at all tangentially. So you're not going to make it go faster or slower in a circle. If these things all cancel each other, you will have no angular acceleration at all. So the thing does not start going faster or slower. And this brought up the static equilibrium stuff, everyone's favorite topic. So make sure that you are comfortable with that. So doing static equilibrium problems, there's a lot of skill that goes into those. And then, of course, we relaxed the restriction eventually that the net torques all had to cancel. If the net torques don't cancel, the object will angularly accelerate. And as far as how much that is, we have to learn about rotational inertia. So rotational inertia was basically how resistant is something to rotational change. Here, you cannot condense the object into the center of mass. You cannot condense a more complicated mass distribution into a simpler one. It's really important that you consider that the rotational inertia depends on mass, mass distribution, and axis of rotation. Until you have specified all of these things, you cannot nail down the rotational inertia that you should be putting in. So not only how much mass it is, but how that's distributed. The big conceptual checkpoint there is that when you put the mass further out from the pivot, it makes it more stubborn to rotation, right? So it increases the rotational inertia. If you bring the mass closer in, it makes it less stubborn, okay? So it lowers the rotational inertia. Now, as far as how to get these values, if you have something which you definitely know is a collection of point masses, you can compute it yourself. So take each point mass, multiply by how far it is from the pivot squared, and then add up however many you have. Make sure it's always additive. There's no such thing as negative rotational inertia. That'd be like having negative mass. That makes no sense. Rotational inertia is the rotational analog of mass. For anything else, just go and flip to the second page of your equation sheet. It'll be there for reference, okay? And if need be, you can, of course, if I give you like a sphere stacked on top of a bar, you can add the sphere formula to the bar formula or something like that, okay? So that's basically the kind of doing the forces stuff again, but in the rotational world. Instead of doing F net equals ma, we do torque equals I alpha. Then we basically went, just like we repeated the force stuff, we repeated energy and momentum as well. So this is where we introduced rotational kinetic energy. And this is also where we introduced angular momentum. So similar ideas. The angular momentum, again, the idea there was if you can isolate the system rotationally, if the net external torque is 0, then you can conserve angular momentum. So again, you're looking for some kind of buzzword that would seem to indicate that that is a reasonable assumption. If you see the words frictionless pivot, that should hit you like a ton of bricks. That's an angular momentum conservation problem, okay? Because that's the only way that you can reasonably isolate something in the outside world is to, from net external torque, is to have some way that something is spinning while being left alone. So, for instance, make sure you can understand the ice skater idea, right? You pull in your arms, you spin faster. Make sure you know how that works. So that basically is it there. We came in and out of the rotational world much faster than we did the linear stuff or translational stuff originally because it's all so highly analogous. Basically what it took homework, let's see, 1 through of 1 through first half of homework 8 was our old linear or translational physics, and then back half of homework 8, 9, and the first half of homework 10 was all that stuff over again in the rotational world. So we basically did it in less than half the homeworks. From there, we moved forward to simple harmonic motion, which again was a mechanics topic. This was the one that I asked you to watch the videos for. This is in some sense a good topic for this because a lot of the things I just kind of don't derive anyway. So first of all, they have definitely much more complicated kinematics. They are definitely not constant acceleration situations. And so for the kinematics themselves, I'm really asking you for concepts only, okay? So for example, if you set the equilibrium of an oscillating system, let's say a mass on a spring. So if I have the mass out here, I have a relatively large displacement from equilibrium. The spring does not like it, so it will apply an acceleration and force to try to bring me back there. And so if I release it from rest, it will speed up as it goes towards equilibrium. However, that acceleration that it had at first is not the acceleration it has the whole way, because remember, by the time you get here, the acceleration and force have shut off. They're perfectly happy. Now you're at the spring's happy place. But of course, you've built up all this velocity on your way there. And so you're going to overshoot it and bounce back and forth. So you'll notice on the final exam practice problems a few kind of just conceptual kinematics questions, to be able to answer those kind of things. When you really want to calculate something about these systems, use energy. So energy is great when you want to relate location to speed. So a change in location will mean a change in speed. Okay? So for instance, in this particular system, you are going to trade your spring potential energy, which depends on location, right? Because the location is going to inform how much your spring is compressed or stretched from equilibrium. And that's going to trade with speed in the form of translational kinetic energy. So that's how you can figure out how the movement along the spring can result in speed changes. For a pendulum, there's no new form of potential energy needed. It's just gravitational potential energy. So as a pendulum swings back and forth, the height of the center of mass will change above the ground. So as you swing to a larger angle, the center of mass will be higher above the ground. When you swing down, it'll be lower. And it goes into rotational kinetic energy, 1/2 I omega squared. Question?
Yeah, I was wondering if you could, regarding the physical pendulums, when you talk about L and R, it's a little confusing because you want to be towards the center for like D com is what it says, or L like L2,
right?
L divided by 2.
Yeah.
But so what becomes is the radius the entire length of the thing?
Right. So here, when you're tracking the potential energy, you always want to track the center of mass, right? So if we're talking about the amount of energy gravitationally that it has, the question is how high is the center of mass of the whole thing above the ground? So if we go to a physical pendulum, let's say a solid bar or something like that, presumably the center of mass is in the middle, right? So that is the point that we are interested in tracking. And so in the equation, H equals R 1 minus cosine theta. This equation is just purely geometric. This equation says if the pendulum has such and such an angle here, it'll tell you how high is a given point above the lowest that it gets on the swing, R is the point that you have to tell it that you're interested in. So R is the distance from the pivot to the point of interest. So if you, for some reason, were fixated on this point right here, and how much this point varied above the ground, you could put in that distance. I don't know why you'd want to. There'd be no particular reason. If I was just kind of being weird on the homework, I'd say you paint a blue dot on the physical pendulum 3/4 of the way down. How much does that vary above the ground? But for all practical purposes, what you're interested in tracking here is the height of the center of mass, right? So if you're tracking the height of the center of mass, then you need to put in how far is that point of interest from the pivot, okay? So in this form, HCOM is almost definitely what you're interested in because that's what's relevant for the gravitational potential energy. And if HCOM is what you want to track, you need to tell this formula that that is how far the decom is from the pivot, and then this will be the angle of the pendulum. So in this case, if I were to call these pendulum of length L, decom would be L over 2, right? So I can't remember, there might have been, I can't remember the homework problems exactly, but I think there was one problem that was like this, where you had to track that point, the center of mass. The thing that makes it a little bit tricky is that when you have a simple pendulum, all the mass is at the end. So the center of mass is here. So if you're trying to track the center of mass there, now that is the entire length of the pendulum. So in this case, decom is L, right? So that's why you use decom as L over 2 on this one and L over here. But the aim was the same. We're trying to get HCOM so we can talk about the potential energy. Another common misconception, I think I was asked about this twice today, so I'll mention it for everybody. So if you have like a physical pendulum, obviously the different parts of the pendulum are all moving at different speed. So 1/2 mv squared is not your friend there. What b do you use? Okay. So luckily, of course, that's why we have our angular kinematics, because at any given moment, all the different parts might not have the same b, but they all have the same omega. So that right here, you're good to go. Okay. So if you want to think, what's the equation that'll always work? 1/2 I omega squared. Now, if we go over to the simple pendulum, there isn't mass all along here. There is only one mass, and it's at a very specific point and has a very specific linear speed at any given moment. So, if we were to calculate the rotational kinetic energy of this, well, we could plug in the rotational inertia of a single point mass is mr squared, and we can express omega that this particular pendulum has in terms of the linear speed of this particular particle, okay? So I guess I'll put it as v over r for the moment, v over r. And if you simplify here, you find that the rotational kinetic energy here is 1/2 mv squared, which is of course equivalent to thinking of this as a single point particle just flying through space, and that trajectory just happens to be a circular arc, right? So there's nothing wrong with treating it with just regular old 1/2 mv squared. The only thing you want to make sure is not to do both. Okay, you don't want to double count. You can think of it as either rotating or as translating, but it's not both. Because if you're thinking of it as rotating around this pivot, the pivot is not moving. So here you would think it's like, okay, well I don't have translational because the pivot's not moving. I just have rotational. So you should never include both forms of energy. That's actually counting it twice. That's double counting it. So that's what you do when you want to calculate something numerically. You You can't use the constant acceleration equations. Luckily, the energy doesn't care if the acceleration is not constant. Of course, the one thing you give up is time, right? So this is one of the few exceptions where the time is so important that I just pull out of thin air what the time is and I hand it to you. I give you the formulas. So the formula is 2 pi squared of m over k for a spring system, and for the physical pendulum, or any pendulum, 2 pi I over d com mg. And I pointed out to you, those are the amount of time it takes to complete one oscillation. So first of all, know what a complete oscillation means. It means every single system parameter is reset and ready to do it again. And one of the things that puts the simple in simple harmonic motion is the fact that if you look at those formulas, there's nothing in there that says how do you release it to start with. So everything in those formulas is intrinsic to the system itself. So you can predict the oscillation period of those systems before anyone ever puts any oscillation onto it, whether it be big or small. Now for the spring, it truly is simple harmonic motion. What amplitude you release it at does not matter whatsoever. Then this is where you remember there's a little bit of an asterisk, because for the pendulum, it really does matter. And so we kind of have our cake and eat it too. We say that the amplitude doesn't matter if the amplitude is small, which is kind of weird because that means it matters, right? So we say that this formula here for a pendulum is highly accurate if the amplitude isn't too big, okay? So that basically covers simple harmonic motion in a nutshell. Again, the 3 major aspects are conceptual kinematics, quantitative energy exchange, and then plug in to the period formulas, know what the period formulas depend on, and just as importantly, what they don't depend on. Okay? And then finally, we talked about waves. So for waves, we focus very much on periodic waves. So not only do they have an amplitude, but they have a wavelength and frequency. They have a period. They have a wave speed. The thing to remember about wave speed is it's set by the medium. Okay, so it's a medium only. We learned some interrelationships between these variables. For instance, we learned that frequency and period are just basically asking the same question in a different way. And then we learned that the speed, frequency, and wavelength are all interrelated. So remember that the V is set by the medium. And make sure you understand why when a wave has a higher frequency, it has to have a lower wavelength. So we first introduced this for a wave on a string. We even wrote down what properties of the string determine the wave speed. So those properties are the string tension, F. We switched to tension, F. And the string linear mass density, mu. When we switched to sound waves, not a whole lot changed. These are all still the same. Of course, the speed of a sound wave has to be determined by the medium. And for this, you can just basically use the value that's kind of considered standard. That's the speed of sound in air at room temperature and atmospheric pressure, which is where we live. Okay, so I talked a little bit about what went into that. But at the end of the day, that is the value you probably ended up using a bunch on homework 12 for anything relating to a sound wave. The amplitude we talked about, there were kind of 2 alternate languages for amplitude for a sound wave. It's a longitudinal wave. You can talk about the displacement of the air molecules themselves, S max, or you can talk about the variation of gauge pressure around 0. So that was called the pressure amplitude. I didn't do much with that on the homework. The only thing you really might need to know that for is this idea that when you have standing waves in sound, that the antinodes and nodes reverse depending on if you're talking about displacement or pressure amplitude. Okay, so if this is an antinode, this is a node, and vice versa. So that's useful if you're looking at the applets that I posted, and in some of the homework problems, they gave you the schematic picture of it, so it's nice to know what you're looking at. Are you looking at a displacement variation or a pressure variation? So that right there kind of was the wave basics. We talked about loudness of a sound wave, and this relationship here will carry you quite far. Knowing how the intensity of a wave, or the loudness, relates to the amplitude. Intensity is proportional to amplitude squared. And when we go over to the decibel side, realizing that every factor of multiplying by 10 will add 10 decibels. So you work this kind of relationship from front to back and back to front. I think there's several homework problems. Some of them ask you to start at amplitude and wind up at decibels, and some the other way around. And then we got to standing waves. And for standing waves, there were two main equations. This one, this was for when the ends are like. So for those, you can fit in any harmonic. The n are the harmonic numbers, any integer will do. Remember what n is counting. It is literally the number of half wavelengths in the waveform. So that allows me to give you a picture, and you'll be able to work backwards to what harmonic that is. If you see 7 half wavelengths, that is n equals 7. V here, if it's a wave on a string, use this equation to calculate the speed. And if it's a standing wave in sound, just use the 343. I also did the equation where there was unlike ends. So one end's a node and one's an antinode. Then you have a different formula. So there's a factor of 4 in the denominator, not a 2. And only odd harmonics are allowed. So n can only be odd numbers. And remember that n in this case represents the number of quarter wavelengths. If you can't remember what the n stands for, it's kind of right in the formula, right? So this is the number of half wavelengths. This is the number of quarter wavelengths. The 2 and the 4 are still in the equation. So again, if I give you a picture of a standing wave and you notice right away that one end's a node and one end's an antinode, you think, okay, those are unlike ends. How many do I have? I have 7 quarter wavelengths. I guess that's the n equals 7 harmonic, and I can calculate the frequency needed to produce it. Okay, so that's basically it. I guess I'm out of time. If you have any other further questions, just drop me a line between now and Thursday. I'll do my best to get back to you.